I'm going to talk about work that we've been doing in safe learning in robotics. And I'd like to frame this problem in the context of really some of the discussions that went on yesterday and that we were having this morning about this blending of safety objectives. And I always think of them as like high performance objectives, using machine learning to really get better models, get a better understanding of the environment, and really do high performance control. But I'm not really a background AI person, I'm coming from control theory, and I've been working in safety control for safety critical systems for a long time. And it's really in the past, I would say 7 or 8 years, that we started to think about, with our colleagues, largely at Berkeley in the Berkeley AI Research Lab, to bring together machine learning with this kind of safety verification. So that's what I'd like to talk about today. And these discussions, especially the discussion yesterday about this paper which recently came out about concrete problems in AI safety. So looking at issues, for example, are you sure you have the right objective function? Even if you do, is that objective function scalable? And then when you're learning how to do safe exploration, these are topics that are very interesting. And it was nice to be able to read, this all in one place, this kind of concrete list of important problems to look at. And I think, in terms of what I've been doing and will present, it's really in the context of safe exploration. Okay, so I come from a background of, I said, control theory. I've been working on air traffic control systems and aircraft control systems for about 20 years now. And this is a safety critical system. It's a human-centered control system. There are air traffic controllers that are watching through radar feeds all the aircraft. In this case, it's the Oakland Center, so it's in the sort of northern Bay Area, aircraft trajectories in sectors, and are talking to pilots over radio channels guiding those aircraft. And there's a lot of structure to the system. So on the left-hand side, you see cross traffic. On the right-hand side, you see traffic merging into San Francisco. Those aircraft are following well-defined jetways in the sky at well-defined altitudes. And there are strict safety critical measures. So the key thing is collision avoidance, of course. Aircraft have to stay 1,000 feet apart laterally, and 5 nautical miles lateral separation and 1,000-foot vertical separation. Okay, and so it's a human-centered control system. There's a lot of structure in the system to manage the complexity of that problem. And if you spend a lot of time sitting behind controllers, it's interesting what they do. They tend to manage the complexity of this problem of dealing with 15 to 20 aircraft at any given time by grouping together aircraft, usually based on some kind of safety metric, like potential conflict. So in this stylized view, you have the aircraft colored in red as a group that an air traffic controller would spend most of his or her cognitive time on to be able to make sure that doesn't result in a collision, and then the aircraft behind the queue. But they tend to get aircraft following the same jetway at the same velocity, so you can basically treat that large group of aircraft as one aircraft. And they tend to organize the control in terms of flight modes. So most of the time, aircraft are flying at the average speed optimal for that altitude. And if they have to separate aircraft, they'll follow, they'll speed it up a little bit, slow it down a little bit, they'll put it into a detour if they need to, and kind of a last result is to put it into a holding pattern. So there's these well-defined modes, like a hybrid system model. Okay, so it's kind of a very safety-critical field. It's slow-moving, it's slow to introduce new technology, but there's a change happening because of UAVs coming into the National Airspace System. And now the funding agencies, the FAA and NASA, are very interested in UTM, Unmanned Air System Traffic Management. If we're going to put these into the air traffic system, how do we design a traffic management system for these UAVs that's, first of all, safe? And safety means we've still got the thing, we don't want the vehicles to collide with each other, but we don't want them to fall out of the sky. We don't want them to land in busy urban areas in an unexpected way. So trying to think about how to design such a system from scratch where we probably want to adopt some of the structure of the current, or some of the notions of the current system, albeit at lower altitudes and in different kinds of airspace. So, the goals of safety, simplicity, that hybrid system representation, but also, these are autonomous systems, so the ability of these is to adapt to new information as they sense what's going on and be able to autonomously adapt is a new thing, and that's really where learning comes in. So I'm going to talk about two things. I'm going to talk about a tool that we've been building for about 20 years now in different contexts of safety-based control, and then I'm going to talk about how we integrate learning methods into this. Okay, so our idea of control for safety. So right now this is model-based. There's no learning in this notion right now. Is the following. If you can define what it means for a system to become unsafe, and you can represent that unsafety as a subset of the state space of the system. So, stylistically, that's that red ellipse that I've labeled the set G at time 0. And if you have a model of the system, and you can backpropagate that set G of 0 under the dynamics of the system, then what you've computed is what we call the backwards reachable set. So it's the set of states that could, of the system, configurations of the system that could reach the unsafe set after some period of time. So you can backpropagate it over different time horizons. And it's a control problem and there are disturbances, so you can use the control to your advantage. You can actually use game theory, so the best possible control for the worst possible disturbance, and you can mathematically characterize and compute these sets. And you can do them in low dimensions, and a lot of the community working on this is trying to figure out how to do this effectively in high dimensions, and new tools are coming online to compute these reachable sets and to use them in real problems. So as an example, this is, these are 4 quadrotors. These are when I was at Stanford, so we called this STARMAC for the Stanford Testbed of Autonomous Rotorcraft for Multi-Agent Control. We maintained that name even when I moved to Berkeley because it's kind of a cool name, and BARMAC didn't really go well. So there are, and these are quadrotors, I don't know if we built them ourselves. This is before the days of ascending technologies and now DJI, and so they're like carbon fiber tubes and a lot of graduate student time in building those. And those are 4 graduate students. They're joysticking them around. And then when the aircraft come within the safety distance of each other, that's computed on board each aircraft, and I've displayed those safety regions. For each aircraft, there's 3 other aircraft, so you see 3 other relative safety zones around it. So if an aircraft touches its unsafe zone, or the boundary of its unsafe zone with respect to one of the aircraft, then the experiment is that the autonomous control takes over and it guides the aircraft away from each other. So the pilots are trying to collide the aircraft, the autonomy takes over and won't let them collide. Okay, and so in this case, in general, if we trust the models that we've used and we trust our computational method, this provides a verification of safety. And so, those are big ifs. We have to have a good model of the system that we trust. Typically, we use simpler models that are over-conservative. We overestimate the effect of the disturbances, the actions of other aircraft that we don't know. We underestimate the effect of control in computing these sets. Okay, so that's, in terms of an experiment to test human transfer from human control to autonomous control, this is not the experiment that you would want to showcase this for, because when the aircraft, when the control moves them so that they're separated again, then control is just sort of given back to the human, and they kind of have to joystick it around to make sure they're actually controlling it. So it's just to demonstrate how you might blend these two together, but not the actual interface of blending them. Okay, so that was an experiment a while ago. You can also turn this problem around and talk about capturing a desired condition. The computation is essentially the same. You can chain link these computations if you have a hybrid system where you're switching modes. So you can reach a target set going back 2 modes, and then you can couple that with an unsafe set to compute what we call this reach avoid set, the set of states from which you're guaranteed to reach a target condition under this mode sequencing while avoiding an unsafe condition, or states that could get to that unsafe condition. And the mathematics is interesting. I think the computation is even more interesting. That's why we've been working on it for about 20 years, because that's hard. It's essentially, flavors of dynamic programming, and so we need good computational methods and good approximation methods for this. And so a large part of my lab is working on effective approximation methods for computing over approximations of unsafe sets and under approximations of safe sets. Okay, and so then going back to the UTM problem, just before we switch into learning, that problem of creating a root structure and thinking about control structures for these autonomous UAVs, if you think about, say, an Amazon warehouse that's in Concord, and then the routes to try to get to different locations in the Bay Area, putting a cost structure over it. So it's cheapest to fly over water, it's most expensive to fly over populated areas. You can easily capture a shortest path problem. And you see this emergence of trunk routes and then short deviations into the heavily populated areas, which kind of makes sense. So these highways in the sky emerge, and we can think about platooning these UAVs along these highways. And so this is a hybrid system model of a UAV in a platoon of UAVs where it could be a leader of a platoon, it could already join a platoon, and the control structure for that. So we used reachability, these backwards reachable sets, to compute the guards for this hybrid system. When it's safe to transition onto a highway, when you have to avoid the other vehicles that may be merging onto the same highways as you. So those transitions are all computed automatically using reachable set tools. And so just some quick examples. Here's just two vehicles, a red vehicle and a blue vehicle joining the highway. The red vehicle is trying to get to a target set while avoiding the unsafe zone around the blue vehicle, and then the blue vehicle tries to do the same on the lower graph. Okay, so that shows that reach avoid operator in practice. If you apply this, now I'm not showing the sets, but they're all applying this kind of control law. You see this kind of organic formation of a platoon, and then things like intruder aircraft that aren't following the rules are automatically avoided, so the aircraft just leave the platoon if they detect an aircraft coming in their vicinity. Okay, so that's what we spend a lot of our time working on. And as I said, we spend a lot of time working on the curse of dimensionality. I'm not going to talk in detail, but just to know there's a research community working in this area. Really largely this is model checking, verification tools when we have interesting physical dynamics of the system. Okay, so now let's just switch into the second part, which is this learning component. We have these, I would call them now filters. They're control filters that as you approach the boundary of these unsafe sets, it's going to filter away your control actions so that you stay safe, so that you stay in the safe zones. Well, then we had the idea, suppose you're just inside the safe set, why don't you just do learning inside the safe set, and then as soon as you get to the boundary, just switch to the safe control. So it's kind of a very kind of simple heuristic of just sort of almost blindly blending these two objectives together. And so safety is always maintained, but performance is heightened if you're inside the safe zone of operation. And so we did the very first experiment. We took a very simple learning scheme, so this policy gradient sine derivative scheme, and we tested it, or we implemented it on our quadrotor. This is just a quadrotor flying inside a room, and we asked it to track a step trajectory, just going up and down, up and down, up and down. But the hard thing is we took the model away from the vehicle, so it didn't know its own model, and it didn't know what control it had to apply. It had to learn what control to apply, but it knew what trajectory it needed to track. The first thing we did, though, was we computed, using the model, we computed the safe envelope. We didn't want it to crash into the floor, crash into the ceiling, so we used reachability, computed the safe envelope, and then we took the model away, and we asked it to learn to track this trajectory inside the safe envelope. So it's somewhat of a contrived example because we used the model to compute the reachable set, and then we took the model away. And so it does what you would expect. It first drops because it doesn't know its own dynamics. It doesn't have a control scheme. But it doesn't crash because it hits the boundary of the safe envelope, and it knows what control to apply to stay inside the safe envelope. And then it kind of starts bouncing up and down on the bottom of the envelope. And in bouncing up and down, it's learning that, oh, if I apply this thrust, I go up. And so after about a minute, it does a fairly good job of tracking the blue dashed trajectory, which is the trajectory that we asked it to track. And it always maintains safety. Okay, so then we started saying, well, if we're doing this, why don't we, and we're learning a better model over time, then we can use these models to update our safety envelope. And now is where, like, as a control theorist who's worked on safety all the time, we kind of get into uncharted territory, right? Because we're saying, well, that means you didn't really trust your initial safe envelope to begin with. And so now I think these are where we start asking ourselves these interesting philosophical questions of what should the learning rate be? How do you combine learning for safety versus learning for performance? And that's really what the kinds of problems that we're trying to work on now. So we're using, typically we're using Gaussian process models to represent the unknown parts of the, or Gaussian processes to represent the unknown parts of the model. So we assume that we have some model, maybe a nominal model of the system, and then we have unknown components in that. And those are what we've so far been using Gaussian process models to represent. And then we learn over time those Gaussian processes that allows us to update the model and then use those to update the safety envelopes. And so here's one experiment. Again, this is the same experiment where, and we'll just, the style of the experiment is the same, but now we're actually applying this safe learning. So the envelope, which is shown in kind of, down in the right-hand corner, it's first indication that the envelope is unsafe. The vehicle is following this trajectory and it violates the envelope. It realizes it doesn't have a good model of its own disturbance, so it scales back the envelope and then starts to learn a better model of itself, so it gradually increases the size of the envelope. So it's changing the size of the envelope over time. And then as a last example of this, this is one of the latest experiments that we did. We actually made it a little more stark. We introduced a fairly large disturbance that the vehicles didn't know about and then asked them to learn this disturbance. So we put a big fan in the room that only affected part of the room and then asked the vehicles or asked one of the, you'll see two experiments running. In one experiment, we used safe learning, and then the other experiment, we didn't use any learning at all, so it was just trying to, stay within the envelope. And you can see the difference in, you can see the difference in performance and safety. So we call this update the online model validation. Okay, so this is basically one experiment which is run twice, and that you can see the fan down in the bottom. And so the vehicles we're slowly tracking the step trajectory here. And so they're basically performing similarly. And so we're using policy gradient reinforcement learning and also Gaussian processes. And we're using the reachability analysis that I spoke about. And then the vehicle, so we've got the envelope computed and safe control associated to that envelope. And so then we ask, what happens? So we don't know about the disturbance, and there is going to be a significant disturbance. So on the right-hand side is the safe learning experiment. So it's got this online validation. And on the left-hand side, we're not using the safe learning. And so you can see what you might expect. As the fan is turned on and the vehicle approaches the fan, in the case where it notices that there's a much bigger disturbance than it expected, it scales back its envelope. And it basically says, I don't understand what the model is here anymore, so I'm scaling back my envelope to my to the data points that last gave me a good indication of what my model was. And so you'll see in the subsequent experiments, they both perform fairly similarly where there's no disturbance, but as they get back to down in the lower part of the room where you see this kind of big disturbance from wind, you'll see a significant change. Well, in the safe learning one, it won't even go there because it doesn't have enough data points to understand how to build a better model, while the other one gets buffeted around. Okay, so as I said, these are steps that we're taking to try to combine together learning in a principled way, learning and safety control. And so to conclude, we're using reachability analysis for safety. Again, that's predicated on We assume we have a good model or a good nominal model and some estimate of the bounds of our uncertainty. We typically use hybrid system models for simplicity when we have a large complex system, and we've incorporated in some first steps the ability to learn from new information. So I think for this workshop and just listening to the talks and the discussion, I think the biggest question for us right now is, in a safety critical scenario, how do you update? What's the really principled way to use the learning to update? Another question which has come up already in our discussion this morning, which I'm very interested in, is we're collecting these large data sets about how UAVs fly around or how cars drive around. Who actually owns this data? What is the setup of this data market? How should that work? And then of course, we have, in our experiment so far, very limited human interaction, but that's a huge component in all of these human-centered systems. So how do we get good representative models or learn statistical behavior that we can incorporate in this safe learning mechanism for human behavior? And we're just working on a number of experiments for this. Okay, thank you.